Hello, welcome to part 2 of our review of basic properties of inversions, where we continue with the examples. So I still wanted to give one more example of the part 2, namely sort of the simplest case, where the line does not go through C, but it is a tangent to the circle of inversion. So again, let C be the center of the circle of inversion, and here is the circle of inversion. And let me take a line M. Note this line does not go through C, but it is tangent to the circle. So what will this line be mapped to? Well, that's actually a very easy situation. Namely, I again draw a perpendicular line to the line, and if I mark the point of intersection by H, then in this case, the point H is mapped under the inversion to itself because it lies on the circle of inversion. So this is H prime. And I already now see the diameter of the circle that is the image of M. So it's just a little circle inside like this. That is tangent to both the line M and the circle of inversion. One thing that is sort of worth noting is what would happen if what happens if you move the line further away from the circle. So if you make, in other words, what happens to this circle, right? So if you move the line further away, the circle becomes smaller and smaller. But what happens if you move the line closer to the center? So this was essentially the second example we drew last time, but this time I wanted to sort of see how this looks in motion. So let me just draw a little animation here. As good of an animation as you can get on the whiteboard with 3 frames. Okay, so here is C, C, and C. So the movie is sort of will move M, the line M, towards C, and want to observe what happens to the circle. So first, on the first picture, we can start with the line M being tangent, like here, and then this is the image of this line. Then if I move the line much closer to C, you see that, well, I don't know exactly how to draw the circle, but I know definitely that the circle has to go through C, and it has to intersect the line at these 2 points. So you see the circle is kind of a big diameter. Right? It's kind of a gigantic circle. And if I finally move the line really close to C, again the circle has to go through these points, so it looks like that. So, as you see, if you move the line closer and closer to the center of the circle of inversion, the image of that line, which continues to be a circle, becomes bigger and bigger. Every time you get a circle that goes through C, but you start with a little one, then get a bigger one, and then get a really big one. And if you continued this process and actually moved the line so it finally went through C, went through the center, this bigger and bigger circle would eventually degenerate into a line. And that's not surprising, because if you had a line that goes through C, you should get a line according to part 1. Lines through C are mapped to themselves. Okay, and finally let's look at an example for part 4. So let's see what happens if you want to map a circle that is not through C how do you get the other circle? So here is again C, and here is the circle of inversion. Okay. All right, so I'm going to take a point somewhere here, let's call it A, and take a little circle centered at A. Okay, as you see, this circle, the red circle, does not go through C. So we are in the situation 4 where we look at a circle that doesn't go through C. I'm going to call this circle calligraphic C, and I want to know. So I know already by 4. I'm not going to go through the proof of this. I want to know. So I know that the image of this circle calligraphic C is another circle that does not go through this point C. But where is that other circle? So I start by drawing a line that connects C and A, and let me denote these 2 points. Let this be B and this be D, just because I've already used up the words, the letter C. So if I could see where this line segment is actually mapped, I would get the diameter of the circle, of this little red circle. So how do I do that? Well, by using the same method we discussed before. So where would A go? In fact, I don't actually need to worry about A. I can just look at B and D. So where would B go? Well, I draw a perpendicular line and then draw a tangent line. And this here is B prime. It is the image of B. So B prime is the image under the inversion of B. Okay, and let D prime be the image under the inversion of D. Of course, you note this line segment BD is part of that blue line, and the blue line goes through C. So by 1, I know that the blue line is mapped to itself. So that means the image of the line segment BD is actually lies on that blue line. So now I just need to figure out where D goes, and I do exactly the same thing. Namely, I draw a perpendicular and then a tangent, and it intersects here. So this now becomes the diameter of my circle. So this here is the image ICK of C. It's sort of interesting to discuss what happens as you move these points B and D in their respective directions. So what would happen if I moved B closer to the circle, to the orange circle? Well, you see then B prime moves closer to the orange circle as well, because remember, that's how inversion works, right? I mean, in particular note, B prime is actually closer to C than D prime, even though B was further away from C than D. Well, that's how inversions work. So if I move B closer to the orange circle, B prime is also going to move closer to the orange circle, and eventually I get these 2 circles being a tangent here. But maybe a more interesting thing is that what happens if I take the point D and move it closer and closer to C. What will happen then? So that means I'm expanding the circle a little bit, still having it go through B, but moving the D a little closer and closer to C. So these circles just become a little bigger and bigger. So what happens is that this point D prime goes all the way in that direction, and eventually, if I actually make this circle extended so that D is equal to C, so that the circle goes through B and then through C, then this whole circle becomes so big that it degenerates into a line. And that's not so surprising, because then we're actually in part 3, right? We have that circles that go through C are mapped to lines that are not through C. And in fact, once D becomes equal to C, the circle will be mapped to a line that goes, through B prime. Okay, let's just again draw a little bit of an animation here, how this would look like. So here are 3 copies of the circle of inversion. Well, maybe I'll just do this vertically now, because otherwise I won't be able to see this very well. So you have your 3 circles of inversion, and I'm keeping the point B the same everywhere. And the point C is, of course, the center. And so here I have a circle that looks like that. Circle closer to C, and circle very, 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 very close to C. So what's the outcome? If I connect these by the blue line as before, then the upshot is that that point here moves further and further away. So this is what you get in the first case. This is my B prime. The B prime is also the same here, but the other point moved further away. And finally here, you would get something really big. Right? So you see how this circle becomes wider and wider, and eventually, if you actually went all the way to C, you would get a straight line. So you would be in case 3.